Hello everyone, I'm Minkle, Marketing Head at MoogleLabs, and it is with great pleasure that we host you today for the webinar Quantum Computing Touching the Basics with Saomya Chaudhury, ML Engineer at MoogleLabs. To start, I will take a few minutes to talk about our organization and explain the format of today's webinar. Founded by seasoned IT professionals, Mughal Labs specialize as accelerators and developers in future technologies to enable digital transformation. We are established in Canada with our development centers in India and Australia. Our experts have helped several clients globally improve their business operations using AI, ML, DevOps, blockchain, data science, Web 3.0, and metaverse. If you need services in this, we would be happy to connect with you at an individual level to discuss the work in detail. As for the webinar, firstly, Mr. Soumya will give a presentation on quantum computing on behalf of Mughal Labs and discuss its overall potential. The webinar will take around 30 to 45 minutes. Then all the participants can take some time to ask industry specific questions. Please feel free to add your questions to the chat as they arise. Mr. Soumya will address them at the end. Also, if you can please keep your screens on to see the presentation as a speaker goes through the various points. Now let's welcome our expert engineer to take over the screen.
As iterated by Minkle. I'm from Moogle, like working, like my name is Saomya Chaudhury and I'm working here at Moogle Labs. And we will, as the title suggests, right, a bit on, we'll be touching some pointers when it comes to quantum computing, and we'll see a few of the basic stuffs relating to the same. By the end of the webinar, you should be able to explain, like, you see the different caricatures on top left, top right, top bottom left, and bottom right. So these are few nice or practical ways wherein beautiful ways you can define these different quantum computing relating stuffs and stuff. So we'll just have a look at those. Uh, before we begin further, on a quick note, we'll start off with a nice quote by Nikola Tesla, one of the legendary minds up until now. He talks about, to unlock the secrets of this universe, one must think in terms of energy, frequency, and vibration. So it's actually a true fact. Not just in in the field of computation or computer science. It's in every field. Computer science, is a derived domain from all the physical entities which we see around us. So it's basically on those lines. This is a very beautiful quote, and I personally like it. So I guess that would be a starting point. And just to reiterate, before going into the stuffs relating to quantum computing, so to speak, quantum mechanics. We should know a bit about the background, what was before that. So I mean, what is the current scenario at this point of time as well, right? The world through Newton's classes, or basically Newton's way of looking at things. So that was the classical mechanics, which we all might be familiar of, right? So it was proposed by Isaac Newton in the year 1687. That's pretty back, right? And talking when he talked about all these principles in his one of the most legendary books up until now. That's the Principia of Mathematica. And just to remind, we as enthusiasts, right, in the field of computer science, in all different domains, so to speak, starting from mathematics, not just limited to maths or science, we are using calculus on a ever-ranging scale, and that was fundamentally discovered, or the first step was taken by Sir Isaac Newton, and it's defined in the this particular legendary book defines all those principles in the particular book. This calculus is also, we might be uh, whoever of us are in the field of ML and data science and stuff, so we are most familiar with these terms. Like we are in day-to-day activity using calculus. So that's again, thanks to him, we are able to comprehend those stuff. So classical mechanics, it's applicable to macro objects, basically humans, anything from humans to spaceships, or not just limited to them, like planets, stars, black holes, whatnot, just name it. So but any object, any macro scale object which can be seen, for that, the classical mechanics is applicable. So it's highly accurate for those scales. Speeds are involving way less than that of speed of light. So speed of light is, we all are aware of that, probably around 2.99 into 10 to the power 8, but we approximate it to 3 into 10 to the power 8 meters per second, something of that sort. So in those highly, like, in those high speeds, right, things are in a totally different scale. So on the right hand side, it's a nice diagram. You can see, starting from like the scale of objects. So be it very, when the scale of objects are very large, like close to the size of the sun or spaceship, or let's say the bicycle itself, right? So these are governed by the principles of classical mechanics. And when we talk about these big objects, right, they are no doubt faster, but no way, clearly, they are no way nearer to the speed of light, because that's the whole idea of it. And the relativistic mechanics deals with very like small objects. Those are in the scale of, as you can see, right, 10 to the power minus 9 meters. So it's something nearer to angstrom, wherein we are talking about the scale of the atoms and stuff, right? So their relativistic mechanics, or something which relativistic, the word relativistic means relative, so to speak, because everything in this universe is compared to the speed of light. So that's how the word comes into play. And then going further, smaller in size, right, and talking about lesser speeds, right, we arrive at something called as quantum mechanics, because in the scale of atoms, we are talking about now, not in the scale of atoms, sorry, in the scale of electrons, so to speak. So they are way smaller, right? So in those cases, quantum mechanics rules. So it's no longer classical phenomena which is applicable. It's mostly into the quantum scale. And it's actually these, all the three play a vital role in formulating the quantum field theory, which is nothing but, when you come to a scale which is in the scale of the electrons, or even gluons and stuff. So these are fundamental particles which are very smaller in size, and they can travel, since they are very small in size, right? They are able to travel very fast, compared to our bicycle, or spaceships. Even the highest limit which the humans have been able to achieve is 21 kilometers per second, and that too on a vacuum space using rockets, right? So that's the idea of it. But compared to light, it's nothing, right? So that's the idea of it. Things get really weird when it comes to very small scale. That's, we'll see in a bit, talking about the quantum nature of things, right? And here's a bit of a video which talks about, on the bottom right corner, you can see the scale. This is in meters, 10 to the power minus 2 or minus 3, something like that sort. Width of the human ear is basically something in the 10 to the power minus 4 scale. So this actually shows a bit of how things are, or the DNA strand which just went by, 10 to the power minus 8. The helium or hydrogen atoms, 10 to the power minus 10. That's the angstrom, right? And we comes going deeper. We have the protons and stuff, which are way smaller, 10 to the power minus 16. And then these are the quarks. Quarks are nothing but the protons and neutrons are together made up of these quarks, right? So they are again fundamental particles, but that's out of the scope of this particular lecture. So we'll talk about it afterwards. So and then going deep down, it's the Planck's length, which is the ultimate length, smallest unit. in this entire universe, which is on a scale of 10 to the power minus 34. And there's the idea of strings. So these strings combine to form quarks. Quarks combine to form electrons, protons, and neutrons, so to speak. I'm sorry, the electrons do not have a quark. They are they are created from strings directly, and the others are part of quarks, and then they coagulate to form atoms. Atoms give rise to, we all know, all the different kinds of stuffs which we see in this universe, or all macro stuffs, so to speak, like me, you, anyone, as a matter of fact. So, brief about the quantum timeline when it comes to talking about in the time structure. So, end of the 19th century, right? Things became like it was mostly in the classical laws were ruling in those in those times, right? 1920, the birth of quantum mechanics, and these are the biggest minds who are the contributors in in the journey of quantum mechanics. So this man, everyone is definitely aware of, Albert Einstein. A few of them probably like myself, who are physics enthusiasts and stuff, might be aware of Erwin Schrödinger and Bohr's, because these are they have proposed the atoms models and stuff. And why we are talking about atoms in this particular webinar is because this is what enables us to do any calculation on this planet. At this point of time, we are watching the screen. Thanks to those atoms, the interactions between the electrons, you are able to see what's visible on the screen. Moving forward, 1927, right? There's this conference as named, I believe. You can check that out. But here, these the ones who are on top, right? They all met together and had a brief idea about, talked about the great, like one of the forthcoming boom in current world, the quantum mechanics and stuff. So 1940, we this year is one of our favorite years, in at least in our field, in the field of machine learning, because this person, Alan Turing, we guess we all know him, the founder of AI, or the father of AI, whatever you call it. So he was the one who asked the most fundamental question, or the first question, saying, "Can machines think?" And yes, of course. And after that, a lot of things have happened thanks to this guy. And uh, moving forward, 1982, Richard Feynman, again, one of the most legendary physicists up until now. He talked about his Feynman diagrams and stuff. So that's mostly into the like how you can go forth and devise a quantum system and stuff. So he wanted to devise a friendly way of interacting with quantum systems. So that's the name. Once a while, you definitely would be hearing that name somewhere coming from someone whoever is interested in physics. 1996, talking about the this year was one of the legendary years because Peter Shor, right? This man, he invented the first algorithm, which is known as the Shor's algorithm for quantum computing, right? And that was primarily for factorizing. So 2001, they were able to first quantum factorization was done. So 2011, D-Waves announced its D-Wave is a company which was jointly founded, or funded by basically NASA and Google. And as it says, right, the first commercially available quantum computing device, but not a universal quantum computer. A universal quantum computer is any quantum computer which is able to do all the sorts of calculations. Like it's universal, can be used for any problem statement. But this was designed specifically for optimization problem. So people who are from my background, or probably others as well, would be able to understand like what optimization problems are, wherein we try to find out the best possible solution to anything, right? So 2019 marks the year wherein talks about Google announces quantum supremacy. We will come back to that point in a while, and that's something very interesting as well. So that's Gartner's basically a curve which they had. I believe we might be aware of Gartner, this particular company. They are like one of the most emerging technological companies. They did propose that by 2023, right, 20% of the organizations of the will be budgeting for quantum computers project. That's compared to less than 1% today. So when we talk about November 2017, this is the source from November 2017. From that day, it was like just the quantum era had just the ideation had just begun, as in realizing the quantum dream had just begun. But by 20 like as and this particular fact is almost very true, because now that I am also giving you a webinar on quantum technology. So yes, people are getting used to what this technology has the potential of solving and stuff. So yes, it has a lot like way it has to uh, have it has to move way forward, but things have been on track, I believe. So we'll see. But a bit about the atoms and their representation. Why? Because we have been talking at atoms, like we know this particular structure of the atoms, right, wherein the one electron revolving around the hydrogen, for hydrogen basically, two electrons revolving around helium, lithium, three electrons, two in the inner orbits and one in the outer one, right, outer orbit. So something in those lines. And then carbon basically showing up like two inside and four outside, right? So all these structures are basically the ones which we are mostly aware of in the terms of atoms, right? We might have seen this friendly representation, but do they look really like that? We'll just check in a while. So that particular representation reminds me, since it reminds me of the solar system, I just put in a bit of representation wherein you can check out. So yeah, this particular representation is something which we might be aware of, right? So, but is it complete? Well, it's no, because the fact is, when it comes to uh, uh, the dual nature, this person, right, D. Broglie, in his paper suggested that elementary particles, right, or electrons, so to speak, can possess dual nature. What that particular stuff means is they can be particle as well as wave. So the reason why we were able to see these revolving around is because these are being considered as particles, right? So you're able to see those particles, but that's not true. I mean, it's not entirely true, but it has a wave nature associated with it. So basically, we need to account for all these four phenomena: position, where the particle is, or velocity, like what's the speed and stuff. So talking about the quantum mechanics, now we'll just particularly enter what we call the beautiful world of quantum mechanics, wherein you can see this particular bunch of water, right? So I'm calling it a bunch of water. I'm not sure how you technically call it, but let's assume it's a bunch of water. So it's in the physics terms, it's called as the wave function, right? So this particular wave function, well, let's say we are taking a portion of it, right? Again, the portion of it contains, if it is of let's say there's a water particle or a molecule. It's actually called as a molecule, so to speak. But the part particle is itself a part of the entire system, right? So this particular entire system is basically the wave nature, right? That's how actually it is, right? And unless and until it drops down and scatters, like we can see when the water drops down and it scatters, right? We see that it's not at just one point, it's almost everywhere, right? So that's how actually the wave nature of any fundamental particle is actually. So we call them fundamental particles or elementary particles, but they have both the natures attached to themselves. So now we'll know how do atoms really look like. On the right hand side, you see those dots, like a beautiful representation of the different orbitals. This is how actually the atom looks like. If you ask me, Soumya, can you give a brief, like a nice picture of an atom? So how would it actually look like? So in this, wherever you see the concentrated points, right? Basically, again, I would iterate that these are not individual electrons or not individual elementary particles, but they wherever you see more denser particles like that, or more dense area, right? Here it's very dense, so that means the probability of finding electron at that point of time, like at that point, is very high, and here it's very low. So that's how it works out. So this particular visualization, you can see that it's rotating because the electron spins on its axis as well, just like the Earth revolving around the axis. So it accounts for all the pictures which we saw earlier. So you can see the nice anti-clockwise rotation and clockwise rotations in specific, right? So all these kind of structures, beautiful structures, define how the atoms actually look like in a real life. Or you can have a picturization, so to speak, just in a big. It's not possible to picturize it, but this is a nice way of representation or an accurate way of presenting stuff. So next, we'll talk a bit on what we talked a bit on the classical part, quantum part. Now we are going to a bit of a have a versus kind of stuff, like talking about classical versus the quantum nature, right? These are various parameters we'll talk about. One is the information storage. So classical bits we are all aware of, right? And the possible states also, since these two are related, 0 or 1. So we know about classical bits which are 0 or 1, or basically that they can be only one particular state at the same time. They cannot be any. But in the case of qubits, right? So information storage in classical computers is in bits, and for a quantum computer it is in qubits, right? So then and the number of possible states are infinite, right? So basically it means that all different possible states are possible. So it's actually 2 to the power n, if you want to iterate it that way. So 2 to the power 1, meaning if there is one particular qubit, then it has the ability to be having two states which are intertwined with each other. That's this 2 to the power 1, that's two states. So 2 to the power 2 meaning four states, 2 to the power 3 meaning eight states. So something in the exponential scale. So this is whatever you see here, right? This is called as the bracket notation, right? And basically, and this is what we earlier was like what I was referring to. That's the wave function, right? A bunch of stuff. So and the alpha and beta here are complex probability amplitudes. So these are the multiplication factors which are able to give you the final result. So this particular calculation itself is a nice way of representing a quantum state. So order of data processing, but we'll not go much on the mathematics part of this. So that's beyond our scope. So we'll just focus on the basics. So talking about order of data processing, you can see sequential. It's very important to remember that every classical computer, the laptop from which you are viewing or the desktop from which you are viewing, the desktop from which I'm giving my presentation, or so to speak, the fastest supercomputer in this world. So all are following the sequential order of processing. However, it could be very fast, because the fact is, in 1 second they might be able to compute a lot of stuffs, or a lot of calculations per second. So, but the main point is it's sequential. For a quantum computer, the things happen in parallel. So the number of states basically represents that many number of calculations happening parallelly. So it's the possibilities become by default become infinite. So that's the quantum advantage, so to speak. And then the calculations in deterministic, because you know what your output is going to be. And here the calculations are probabilistic, because as I said, because of these alpha and beta, it's probabilistic, because as I said, complex probability amplitudes. We're not going to talk more about those here. So operational capability, classical computers can work in room temperature, in your house, my house, or so to speak, your office, anywhere. They are able to run everywhere and anywhere, right? So, and you know that your computers, or our computers, become after running it for some time, it becomes hot and like hot. So basically, that's the operational capability of a classical computer. And but the fact is, quantum computers need really ultra cold temperatures. And when I say ultra cold temperatures, it's in the scale of near to 0 Kelvin. I'm not sure how many of us are aware of the Kelvin scale. 0 Kelvin is nothing but translates to minus 273.16 degrees Celsius. That's very, 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 very cold, so to speak. The coldest place, it's even colder than the coldest place in the entire universe. So the operating temperatures for a quantum computer which is required is just above 0 Kelvin. So it's just minis, like something in micro Kelvin. So it's not even like it's even less than 1 Kelvin. So it's in micro Kelvin. So, and that's because we need to avoid any kind of interaction or any kind of heat dissipation, because you know that in any appliance, like in any electrical appliance nowadays, uh, we are the factor is heat. The biggest concern is heat. So the most of the energy is being lost in terms of heat. So quantum computers cannot have that, just because they have to have that quantum nature retained. So that's the idea of it. So error rates in a classical computer, it's very low, because as I said, it's again relating to the previous point. They can operate in any kind of temperature, so to speak. For for a quantum computers, these are comparatively very high, because as I said, if we are not able to have a quantum system which is not interacting with with the external environment, then it might actually lose its original nature, or original quantum nature, so to speak. And randomness. Classical computers, whatever random numbers which we generate, the random functions which we use in Python or any type of code, are all at the back end, working in one or the other sort of algorithm based. And whenever you hear that word, right, algorithm is nothing but a procedure of anything. So if there is an algorithm for anything, that means it is not random, because for a for randomness to work in its true potential, you should not have an algorithm to be governing a particular stuff. So it's definitely able. So whatever systems which we have at this point of time in as the current technology, we are able to have pseudo random numbers. But I mean, they are able to generate or simulate randomness, but they are not true, not random. But for quantum computers, since as I mentioned, if we have lot many number of bits, let's say 8 number of bits, right? Or suppose there are 8 qubits, right? So 2 to the power 8. So basically, all the total number of numbers, you can actually generate a random number, because it's all possible solutions at the same time. So whatever you tap in, you find out that's true randomness. So that's the potential of a quantum computer. And a bit on the part of bit versus a qubit maze, how it could actually look like. So you can see that for every iteration, right, the ball in the bit section, right, it goes like one step, like so in total there are like 5 to 6 steps on this, but due to the nature of the qubit, right? Or quantum bits, right? So it's able to bifurcate itself as per the given conditions, right? So it's able to make waves. So as I said, it's mostly like a wave. So I guess the ball notation would not be a good way of representing here, but imagine I'm pouring a liquid from here, right? So if you know that the liquid will spill to the left and also to the right at the same time, and then spill down. So imagine it in that term. So I guess that would have been a easier representation of qubit. So that's how the power of qubit can be realized. So here it since to find the correct optimal path. So we talk about the best case, worst case scenario, right? In terms of algorithmic analysis, right? So the worst case scenario was being shown in the classical bit, which was probably it was taking somewhere around 1, 2, 3, and 4 or 5 steps, right? So here, on the other hand, it took around just 3 steps to. So the best case of classical bit becomes all the cases of quantum bit. So basically, in those categories or in those terms. So a bit about the background of the qubit. So we were already referring to this word qubit from the start itself, basically talking about in terms of the full form is a quantum bit, right? So fundamental unit that carries the quantum information can be 0, 1 or 0, 1. It's a this we will see it's called as the superimposed state. So it can be 0 and 1 at the same time. So basically there could be various kinds of qubit, so to speak, based on their spin factor, ions, and photons. So spin and ions are nothing but basically like imagine the first few slides where when I talked about the planet based model of an atom, right? You know that the Earth covers its day and night series in 24 hours. I mean, it spins at its own axis in 24 hours, right? 12 days, sorry, 12 hours of day and 12 hours of night, right? So, and it also revolves around the sun in a period of 365 days, right? So basically, the spin is nothing but the electron spinning its on its own axis, right? So point when it points up, that's the zero state. When it points down, it's the one state. So we need what we see, what we call basically the two different states in order to devise a quantum bit or qubit. So that's actually the reality is there's no special thing as a special electron. Every electron is a quantum bit on it by itself, right? So it's just that up until now, right, the kind of systems which we have been dealing with, they are all classical based, because we were only able to either measure 0 or 1, right? But not something in between. So the ions phase is nothing but the orbital kind of stuff. So wherein the electron receives an energy. So it's the earlier firstly it's in the ground state. It receives energy or a photon. It bounces to the first the different orbit, right? That's basically the excited state or the high energy state or the one state, whatever you can call it, right? Then we are even talking about photons. Photons, I guess, people who are from the physics background might be aware of. It's the fundamental carrier of light. So, I mean, the carrier of light, so to speak, right? The photons, and photons have something called as vertical and horizontal axis. So, wherein the photons travel in these two axes, and we talk in terms of bit on the polarization stuff. So polarization helps to segregate the vertical and the horizontal part. We are not going to talk more about it, but just a pointer that you can even photons can be used to simulate a quantum bit, right? So based on their vertical and horizontal components. So now coming to the quantum superposition. So we were earlier talking about the 0 and 1 state can be at like which the qubit can be at the same time, right? So that's what we call it as superposition, right? So it actually results from the dual nature of matter and radiation, so to speak. So and it's because of the non-zero probability of an electron to be in more than one distinct state. We earlier saw a bit. So on the right hand side, it's a beautiful picture of an experiment called as the a funny experiment, the Schrodinger's cat, wherein we suggested that wherein they suggested that until and unless we open the box. So this, you see there's a box, right? And let's say there's a poison inside this box, and there's a cat, right? And the poison's bottle has been broken, right? So what's until and unless the box is open, the cat is living in both possibilities, like 50% alive and 50% dead. And that's the fundamental nature or fundamental question which they asked. That's which brought in the quantum phase, because it can be alive and dead at the same time unless and until it is observed by opening the box. Just in a similar case, the moment we open the box, it you can know for sure that the cat is either dead or alive, right? Probably it might be dead. So that would be on a 0 state, or it might be alive on a 1 state. But until that happens, it's in both the states at the same time. That's the whole point of it. So that's the third point, what it suggests, like until it's measured. What's that measure? Basically saying 0 or 1 at a specific instant of time. So something in those lines. So all possible states at once. So we are we saw the bracket notation, something in these lines. So it's there are uh, two qubits. So possible number of states at 2 to the power 2, that's 4, 1, 2, 3, and 4, right? And these are the complex probability amplitudes which are basically multiplied, and this entire system is perfectly a qubit as well. So that's the whole idea of it. So and they are in a superposition state until and unless they are measured. So then we will be talking about quantum decoherence. This particular phenomena is there's a short video to it. I believe you'll be listening to that as well. But before that, a bit of a background. Decoherence, as the word suggests, it's something in relating to inconsistence, right? So basically, when we are trying to devise a quantum system, right? The problem is it's as I said, we need to have the electrons in such a manner, or we need to keep them isolated in such a manner that they are not in prone to any external conditions, right? So we will see in this particular small video wherein there are subtitles, I believe. So I guess you would be able to see what this phenomena is. That was a brief presentation on the quantum decoherence. So as it talks about, until and unless the quantum particle is uh, uh, whenever let's say there's a qubit, and there are the external disturbances at that point of time. What happens is um, uh, basically all these external factors combiningly uh, um, the quantum nature of the particular particle goes off, and I guess that should be a bit on the decoherent side of things. Now, going further, talking about the quantum entanglement, basically this particular section talks about mostly in terms of the there if there are two different qubits, right, which are far apart from each other, right, and they are sent even galaxies apart, right, uh, basically they are still invisibly connected to each other. So that's what entanglement theory talks about, and that's very surprising, and they have actually named it it's quite spooky. So I mean, it's ghostly, so it happens in almost an instant. So when we talk about in terms of, let's say, two different particles which are uh, one is at one end of the universe and the other one is at the other end of the universe, and the link, let's say, initially the particular link is established, then once one particular once one of them breaks the particular measurement, right, the other also flashes the information. So there's a nice a caricature to it wherein it talks about Alice and Bob having sent the message on two different sides, right? And they are, let's say, let's assume that Alice is in probably in one of the galaxies, and Bob is in another different galaxy. And they, first of all, they create a link between these two particles, right? And that is actually created using the electromagnetic radiations. This particular link is established, and then let's say for some reason Alice and Bob have to separate. One has to go outside this to another galaxy, and this Bob remains here, and they want to know instant, like they want to have a message transmission between themselves, right? So they would be able to do that almost instantly. That happens way faster than the speed of light, so to speak. So and they once the link breaks between these two entangled particles, right, particle A and particle B, both of them would be able to see what the message actually was. So that's how the entanglement works out. So how does that actually happen? So these are two different qubits, you see, right? A laser or electromagnetic radiation, so to speak, you're able to throw on them, and these two are intertwined with each other with a link, right? Once this link is created, you can take them far apart, right? One can take this this is an invisible link which is created. Suppose Alice and Bob are taking these far apart. So, and at end of the day, what they do is one tries to manipulate it, as in they one is able, like, let's say one is trying to measure it. Then in that case, whatever information is is seen by Alice, right, the that same information can be retrieved by Bob, that Alice has already seen this message. So something in those lines. So that's how the quantum entanglement um, uh, phenomena works out. So there's a nice cartoon representation of entanglement as well. I believe this particular video's audio you might not be able to listen. I'm not sure whether it might not. So I'll once when I share the presentation, you might be able to check that out. But as of now, I'm skipping it, I guess. Next, coming to quantum supremacy. So if you remember in the timeline slide, we were talking about Google establishes quantum supremacy in the year 2019. So this particular slide will be talking about that. So mostly it is in terms of the quantum, also known as the quantum advantage. And yes, what quantum supremacy talks about is if a programmable quantum device can solve a problem that no classical computer can solve. What does this classical computer mean? Basically, our own laptops or desktops, or so to speak, supercomputer of sorts, right? If no classical computer can solve it in that particular feasible any feasible amount of time, right? So then basically that particular stuff is known as quantum supremacy, because a quantum computer can solve that within a feasible amount of time. So 2019, Google established it using surprisingly just 54 qubit processor, right? So earlier, you remember we were talking about just a 54 qubit system would be able to have the number of calculations that can be done by this 54 qubit system is 2 to the power 54 of the sort. So that's something like 10 with something around 16 zeros, right? So that's the capability of the a qubit processor, right? So unless we know that the same calculations can be carried out, we have the various i3, i7, i9 processors nowadays, right? So these are coming with billions of transistors in them, and these transistors are nothing but fundamentally they are calculations units, right? So end of the day, all we are looking for is making calculations, right? So the number of calculations that's possible in this particular system is close to 2 to the power, sorry, 10 to the power 16. And that's precisely why these processors are able to beat one of the best supercomputers in the world as well. So given the same feasible amount of time, right? So time taken by this best supercomputer, just to be on the same scale, it could be around 10,000 years. So yes, and I guess we might be aware of how the processes, like how big are the processes for a supercomputer. Basically, it's nothing but I mean, it's imagine just one processor being one brain. So a supercomputer is nothing but utilizing let's say a millions of brains to do a particular calculation. So that's how they are able to cut down on time, right? So basically that's what happens. So something, let's say something which would have taken a million seconds, right? With a million brains, it could be done in 1 second, right? So something in those lines. So a quantum computer with just 54 qubits, we was able to achieve that target in 200 seconds. So that's a record. And yes, that's what quantum supremacy talks about in its essence, right? Now, basically, that was a bit of an interesting, folks. If you want, you can have the reference paper, which talks about the article as well. So that's the idea of it. And on a pleasant note, just to end things. So basically, a nice slide which reminds me of this great one of the greatest minds work on this planet. The important thing is to never stop questioning. And yes, of course, curiosity has its own reason for existence. And with this, I leave both you guys to ask a few questions. And in the meantime, I would probably also, while like I'll be shifting the mic to Minkle, who has something to say, and then have like while we'll be having a nice discussion or question round here, I'll actually demonstrate why what are the basically the limitations of classical computers. So yeah, thanks guys. That would be it.
Hello everyone, it's me again. Before we move to the question answer round, I would like to take a few minutes of your time to talk about our company, Mughal Labs, for those who have joined a bit late. Mughal Labs is a brainchild of experienced IT professionals who work towards the digital transformation of their clients' business operations using the latest technology like AI, ML, DevOps, blockchain, data science, and metaverse. Through the webinar, we aim to help others know the power of latest technology. And if you ever need an IT company that supports this technology, We would be happy to help you to decode innovation and improve your business efficiency. Now that's out of the way. Mr. Soumya can take over from here and answer questions in the chat.
Thanks, Minkle. Let me see. I believe in the meantime is when if you guys have questions. Yeah. Uh, Let me share my screen. So, just a brief confirmation, guys. Can you see the other screen which I've opened up, the Chrome window? Minkle, could you confirm in the meantime?
Yeah,
Yeah,
yeah.
great. Yeah. So, guys, just a quick note why things are necessary of the sorts. Just keep a note of this. So, this is a particular program of factorization, right? Factoring stuffs, right? We might be aware of these, doing factors and stuff. So, factors are nothing but basically fundamental units wherein you can make what that particular number is can be divided by, right? So just a brief on probably if we go for a very small number, let's say starting off with one digit number, factors of seven, we know seven is a prime number. So it was almost an instant. So talking about in a bit on a larger scale, right? Again, it's very instantaneous. Like we are able to derive factors of a random number, which is a four-digit number, let's say, right? And talking in terms of, let's say, 1, 2, 3, 4, 5, 6, 7, 8, eight-digit number. Again, you can see for an eight-digit number, it takes a bit of time, right? But it's almost again instantaneous. But the now that we move to this is a nine-digit number, and I just pasted it from the largest nine-digit prime number. This is the largest nine-digit prime number. We're going to find out a factor for a prime number in this case, right? So basically, I guess we might be aware of what a prime number is. Basically, a number which is divisible by one and itself, right? So the number of there will be only two factors. So this, guys, is the key to cryptography as well. Some of us might be aware of that, right? So cryptographic codes are mostly in the scale of prime numbers. So it while it takes like while it is trying to calculate the factors, I would probably if any of us have questions, they can actually go for and ask me, and because it would definitely take some time to go for then check for the factors.
If anyone needs presentation, please drop your email in the chat and we will send you as soon as possible.
So guys, any questions relating to the same or any thoughts? Yeah, sure, Gary. About applying the fact about how like Gary has a question how we see ourselves applying quantum computing. So basically we just that's why I was about to show that particular stuff. So you can see, right, this particular big nine-digit number, it took almost like 2 minutes and 3 seconds to find a factor of this particular number, where which are basically nothing but one and the number itself, right? So it took that humongous amount of time. So I just can't even imagine if I put in a 10-digit number, the complexity goes on an exponential scale and it jumps up. So it would probably in the 8 minutes or 9 minute scale. So in the field of applying like in the field of quantum mechanics, wherein things happen very quickly, wherein we can have all different sorts of combinations at the same time, right? We can definitely go forth and reduce any kind of these time constraining stuffs or basically optimization. So earlier we were even talking about the optimization problem, right? So the optimization problem is nothing but any problem which can have the least possible like time time as a solution to it, right? So these kind of problems are very challenging when trying to solve on a complex level. So so they are also since they are challenging, these problems can be taken up not by a classical computer. They can be taken up by quantum computers itself. So quantum computers would be assisting us in answering these questions. And there are a lot of curious questions wherein we talk about specifically protein folding and stuff. These are biology related questions wherein things are happening. Like we talk about drugs, right? We are not able to if you remember, there is a very yeah, there was a time wherein we were talking about the drugs, the COVID drugs was, it took like 4 to 5 months to develop, right? So these drugs can be manufactured on a very quicker scale than the others as well. So yeah, um, that's the idea of having or applying quantum computers. So Vaibhav has a question saying, uh, we have excellent computation capabilities nowadays. What problems are quantum computers suitable for? Yeah. So, Vaibhav, nice question again. Just we just iterated it. So there are some challenges when it comes to talking about like the optimization problems we were talking about. Then the questions on whether we are solving the complex matrices in the field of mathematics. We can solve those particular problems. And in the field of specifically talking about in terms of the ML scale, right? The those kind of problems which can be dealt with deep learning and stuff can be easily achieved using quantum computers once they are in market as well. So that's a nice question, so to speak. I hope I made clear on that part. So e-commerce is a dominating channel today. What are your comments on this particular domain? Is it applicable there apart from the theory you presented? Yes. Basically, Gary, yes, it's almost applicable in all different sectors, as I said, right? For just for the ideation of faster processing, because the fact is nowadays it's kind of challenging when it comes to understanding about the various relationships between various domains, so to speak. So things are more into so plotting graphs and stuff. So in like if we might have a background on, I guess, the graph theories and stuff, we can actually connect the dots and go forth and help definitely these all sort of problems can be sorted out using a quantum computer. But again, there are some places wherein the classical computers rule. However, we won't be needing. In fact, as I mentioned earlier, quantum computers are as I guess I might not have mentioned it, but classical computers, which are based on zero and ones, are basically on a special case of quantum computer, because classical deals with zero and one individually, but quantum deals with these two states, along with that all the different mid channels as well. So yes, that's the whole idea of it. I hope that was a bit clear, Gary. So great. All right. So do we have any other questions, or should all right. I guess that should be it. And thank you so much, everyone, for joining in. And I believe I'll just end it here. And I hope things got sorted a bit when it comes to quantum computing and stuff. So thank you.